Hi everyone, Mrs. Nowakowski here. Today we are going to continue working on solving log equations. So up until this point, we already know how to solve basic log equations, like the two that are given here. So in that first one, the log base x of 64 is equal to 3. We're solving for the base. The best way to approach these types of problems is to put it into exponential form. Right now it's in logarithmic form. So to change it into exponential form, we're going to rewrite it as x cubed is equal to 64. Since we are solving for x, and x is cubed, we either want to take the cubic root of both sides to cancel out that x cubed, or we can raise both sides to the reciprocal power. So in this case, we're raising it to the 1/3. Remember, an exponent of 1/3 is the same thing as taking the cubic root of a number. So we'll get that x is equal to 4. And for the second equation, this time we're actually solving for the exponent part. So remember, log is just a fancy way of saying what exponent. So this is asking us what exponent must you raise to get 64 as an answer. Some people can do that in their head. If you can't, rewrite this in exponential form. So we get 2y, or 2 to the power of y is equal to 64. Again, if you can do this in your head, that's great, but this is also a case where you try to get a common base. So I am going to rewrite 64 with a base of 2 instead, so that's 2 to the 6th. And in order for 2 to the y to be equal to y to the 6th, y must equal 6. So today we're going to continue solving these log equations, but there's just going to be a little bit more to them. But the nice thing about the log equations that we're going to be working with today is there are actually just two types. And if you can identify which type you are working with, it will make the problem a lot easier because the steps for that type of problem are the same. So the first type of log equation that we're going to be working with is when every single term has a log. So if you look at example 1, we have log base 5 of 4 plus log base 5 of 3 is equal to log base 5 of x. So if you notice, every single term of this equation has a log. And we also want to check, and this is actually the first step in this for these types of problems, we want to also make sure that every single log has a same base, because you can't use the properties of logs unless all the logs have the same base. So every single term, for example 1, has a log base 5. So now we're going to use the properties of logs to combine the terms on each side of the equation. So the goal for these types of problems is to get a log on one side equaling a log on the other. Whatever that base, the bases will have to be the same. The arguments might change depending on the problem. But your goal is to get one single log on one side equal to a single log on the other side. So when we go and look at example 1, we're going to use properties of logs. So remember, if you see two logs being added together with the same base, that is going to indicate that we have multiplication. So log base 5 of 4 plus log base 5 of 3 is the same thing as doing log base 5 of 4 times 3, which is log base 5 of 12. So now we rewrote this example so that we have a single log on the left side and a single log on the right side. Once we have single logs on both sides of these equations, the only thing, if you look at this, hopefully the answer for x would be a little bit obvious, but log base 5 of 12, in order for it to equal log base 5 of x, what does x have to equal? Well, doesn't x have to equal whatever the argument is? So once you get to this point, you can actually ignore the logs and just set the arguments equal to one another. So in this case, x is going to equal 12. The final thing that you should always do is check that what you got for x does not make any of the arguments negative or 0. So when you go back and plug this in, if you plug in 12, we have log base 5 of 12. Since 12 is positive, it doesn't make the argument negative, so 12 is a valid answer. So moving on to example 2, please notice that first, every single term is a log base 7. So every single term has a log, and all the bases of those logs are the same. So again, our goal for these types of problems is to get a single log on one side of the equal sign and a single log on the other side of the equal sign. So on the left side, we already have a single log, so we don't have to worry about that. So we really just have to work with the right side, and we're going to use properties of logarithms to combine these into one single log. So first thing before you do it, because there's two things that you should notice. One, that you see a plus sign between the two logs, which indicates multiplication, but there's also numbers in front of both of these logs. You actually have to deal with those numbers first before you multiply the two logs together, or the two arguments together. So if you remember the power rule for logs, the number that's in front of the log is the same as raising that argument to that exponent. So it just goes back into the argument. So now we really have log base 7 of 32 to the 1/5 and log base 7 of 25 to the 1/2. I'm going to simplify this a little bit further before I combine. So 32 to the 1/5. When you raise something to a fractional exponent, remember that's just a radical. So 32 to the 1/5 is the same thing as the 5th root of 32, which is 2. And 25 to the 1/2 is the same thing as the square root of 25. So that just simplifies to 5. Now that we dealt with those exponents, we can add the two logs together, which is the same thing as keeping one of the logs and multiplying the arguments together. So 2 times 5 is 10. And now we met our goal where we have single logs on both sides of that equal sign. So in order to solve for what x needs to be, since x is in the argument, you can ignore the logs and just set the arguments equal to one another. And your final step is make sure what you get for x does not make the arguments 0 or negative. So the only place that x shows up in this argument is here. So if you plug in 10, 10 is positive, so 10 is a valid answer. Our next type of log equation is when every term has a log except for one. So if we look closely at example 3 and example 4, we have two terms with logs, but one term that doesn't have a log. And same thing with example 4. We have two terms with logs, but something, the third term or what it's equal to does not have a log. So when you start solving this problem, the first thing that you want to do is you want to have all of the logs on one side of the equal sign and anything that does not have a log on the other side, and it should be equal to one single number. You also want to make sure to check to see if you have a common base, which in example 3 and example 4 we do. Example 3, they both have a base of 3. In example 4, they both have a base of x, which is what we're trying to solve for. So the goal for this type of problem is you want to get a single log on one side equal to a number on the other. So only one term is going to have a log, and it's going to equal a number. What you really want it to look like are these basic problems that we did at the beginning. So if you notice, they have one log equaling a number, one log equaling a number. So that's what you want to try to turn it into. And you are going to, again, use the properties of logs to do that. So looking at example 3, we have log base 3 of 2 plus log base 3 of x plus 5.5. So 2 logs with the same base being added together. So using the properties of logs, we're going to keep the log and multiply the arguments together. Remember, when you are multiplying these two arguments, it's 2 times a quantity of x plus 5.5, so we have to distribute. So that argument is 2x plus 11 when you multiply those two together. So now we met our goal where we have one log on one side equals a number. So let's go back and refresh our memory using the 2 review problems that we did. Whenever we had a log equaling a number and we wanted to solve for either the base or the exponent or the argument, it doesn't matter. Didn't we always change it to exponential form? So that's what we are going to do for this problem as well. So let's rewrite this in exponential form. So it's going to be 3 squared is equal to 2x plus 11. So we'll get 9 is equal to 2x plus 11. When you subtract that 11 over, we're going to get negative 2 is equal to 2x. And x is equal to negative 1. Our final step is we want to check to make sure that what we get for x doesn't make the argument negative. So some people think that the value of x cannot be negative, and that's not true. X can be negative as long as it doesn't make the argument negative. So let's see where we're going to be plugging in that negative 1. We're going to plug it in right here. And when you plug it in, you're going to get negative 1 plus 5.5, which is positive 4.5. So the argument is still positive, which means negative 1 can work as a solution. All right, so moving on to example 4. Again, we already talked about how we have 2 logs on one side equaling a number. The bases are the same. That's actually what we're trying to solve for. So the goal for this problem is to get a single log on one side of the equal sign and just a number on the other side of the equal sign. So before we multiply, because we do see addition again, so when you're adding 2 logs together, you multiply the arguments together, but both of these logs have a number in front, so this is very similar to the example 2 that we just did. We have to first move these numbers back into the argument before we start adding the logs. So we have log base x of 256 to the 1/2 plus log base x of 2 squared. I'm going to simplify this a little bit. 256 to the 1/2 is the square root of 256, which is 16, plus log base x of 4. Now that we simplified that, we can add those 2 logs together. So when we add the 2 logs together, we keep 1 log and just multiply the arguments together. So 6 times 4 is 64. So now we have 1 log on one side, a number on the other. So it really just turned into one of those basic equations that we were solving earlier in this chapter. So I'm going to change this to exponential form. If you need to, I think some people prefer to have the log on the left side. So it's a little bit easier to change it to exponential form. So we have x cubed is equal to 64. So to solve for x, you are either going to take the cubic root of both sides or raise both sides to the 1/3. So the cubic root of 64 is just 4. Also, one stipulation is that your bases can't be 0 or negative, so you still want to check to make sure that what you got for x doesn't make the base. In this case, if you notice, they're the bases, either 0 or negative, which it doesn't because it's a positive number. So 4 is our answer. So now that we went through the different types of problems, I suggest pausing this video and trying these practice problems on your own first. And then once you're ready, you can restart the video and I will talk through a few of these problems. All right, so here are the solutions to the first 4 practice problems. These solutions will also be posted in Classroom, but I just wanted to talk through a few of these problems. And again, hopefully you tried some of these on your own first. So when you approach these problems, first identify what type of problem that you have. So if you are looking at number 1, you notice every single term has a log. That is going to be different than how you approach a problem like number 3, where one term does not have a log. So for number 1, when every term has a log, remember your goal is to get a log on one side and it's equal to a log on the other. So using the properties of logarithms, you are going to simplify these logs and combine them into one log. So for number 1, you see addition. So that means you're going to keep one of the logs, multiply the arguments together, so 4 times 14. Once you get one log on one side and one log on the other, like we have here on this step, then you can ignore the logs, set the arguments equal to one another, and solve for x. And your final step is make sure that when you plug 59 into x in the original problem, it doesn't make that argument negative. 59 minus 3 is not going to be a negative number, so 59 works. So number 2 is similar to number 1. Every single term has a log, so we want to combine. So we're really just going to work on the left side because there's 2 logs there, and we want to combine it into 1. This time we have subtraction. So the property with subtraction is actually you divide the arguments. So log base 7 of x minus log base 7 of 3 is log base 7 of x over 3. Now that we're at this step and we have one log on one side and one log on the other, we can ignore the logs, just set the arguments equal to one another. So that's where the x minus x over 3 is equal to 2x plus 4 comes from. And we're going to solve for x. Now, when you solve for x, you get negative 12 over 5. We want to check our answers. When you go back and plug negative 12 over 5 into this log, you are going to end up with a negative argument, which means negative 12 over 5 does not work. It's an extraneous solution, so there's actually no solution to this equation. So it's really important to check your final answers. Number 3 is a different type of problem where it's equal to a number, not another log. So the difference is you still want to combine, you want to have all the logs on one side of the equal sign, and you want to combine them into a single log. So since we have addition, that means we're going to keep the log and multiply that x plus 3 and that 5 together. Make sure you distribute. So we're going to get log base 2 of 5x plus 15 is equal to 7. Once we have one log on one side and it equals a number, then you are going to change it into exponential form. So it's 2 to the 7th is equal to 5x plus 15 and solve for x. We got 22.6. When you plug that in, we still get a positive argument, so 22.6 works. And lastly, number 4, this is a problem where you already have a single log on both sides. So eventually we're just going to ignore the logs and set the arguments equal to one another. But before you do that, because there is that 1/3 in front of that log, you have to make sure to move that 1/3 back into the argument. So 1/3 log base 4 of 125 is just log base 4 of 125 raised to the 1/3 power, which is a cubic root, so that's just 5. And now that we have one log, a single log on both the left and the right side, you can ignore the logs, just set the arguments equal to one another, and just be sure to check your answer. 5 keeps all the arguments positive, so it works. So for number 5, we notice that we have a log in every term. Now there's no written base there, which means we have a base of 10, so that's your common log. So the bases are all the same. So the goal for these types of problems is we want one single log on one side of the equal sign and a single log on the other. So we really just need to work on the right side. The first thing we have to do is move the 1/4 and the 1/2 back into the argument. 16 to the 1/4 is just the 4th root of 16, which is 2. And 49 to the 1/2 is the square root of 49, so that's 7. Once you get to this step, you have 2 logs being added together, so you keep the log and multiply the arguments together. And now that we have a single log on both sides of the equal sign, you can ignore the log, set the arguments equal. So we get y is equal to 14. Make sure it doesn't make the argument negative, which it doesn't, so 14 works. Number 6 is a problem where we have a term that does not have a log. So we want to get a single log on one side and have a number on the other side of the equal sign. So since we have 2 logs with the same base being subtracted, then we're going to keep the log and divide the arguments. So we get 9x plus 10 over 5x. Now that we have, I just switched the order around and put the log on the left side. So we have log base 3 of 9x plus 10 over 5x is equal to 2. Whenever you have a log equaling a number, we want to change it into exponential form. So that's 3 squared is equal to 9x plus 10 over 5x. And 3 squared is 9. We're going to multiply both sides by 5x. So we get 45x is equal to 9x plus 10, and when you isolate your x and solve, you're going to get 5 over 18. And again, just double check, make sure it doesn't make any of the arguments negative, which it doesn't. 7 is very similar to number 6. We have logs on one side, but a number on the other, so we want to combine those logs into a single log. The first thing we want to do is bring that 2 back into the argument. So we get log base 2 of 3 squared, which is log base 2 of 9. Once you have simplified that, you have 2 logs with the same base. I actually think I forgot to write the base right there. Being subtracted, so you're going to keep the log and divide the argument. So you get 9 over x plus 1. So now we have a log equaling a number. Change it to exponential form, so that's 2 cubed, which is 8, is equal to 9 over x plus 1. We're going to cross multiply or multiply both sides by that x plus 1. Make sure you distribute that 8. So we get 8x plus 8 is equal to 9, and x is equal to 1/8, which still makes the arguments positive, so that one works. So the last one I want to go through is number 8, because this is the one example where the bases actually aren't the same. We have 2. Initially, this looks like the type of problem where every term has a log, but if you notice, 2 of those logs have a base of 3, but this one has a base of 7. So since we have different bases, we have to be careful with how we approach this, because we can't approach it in the same way that we would number 5. Because the bases are different. But remembering our properties of logs, when you see log base 7 of 7, so log, remember that log means what exponent. So what exponent must you raise 7 to get 7 as an answer? And that's just 1. So we can actually change that log base 7 of 7 to just a 1. So now this turns into a problem where we have one term that does not have a log. So I want to get all of the logs on one side, so I'm going to subtract that log base 3 of 8 over and subtract the 1 to the other side. So now we have 2 logs, same base, being subtracted. So I'm going to keep the log, divide the arguments, and whenever we have one log equaling a number, we're going to change this to exponential form. So we get 3 to the negative 1 is equal to x plus 5 over 8, or 1/3. Because remember, 3 to the negative 1, negative exponent means reciprocal. So 1/3 is equal to x plus 5 over 8. I'm going to cross multiply. So we get 3x plus 15 is equal to 8. 3x is equal to negative 7, so x is equal to negative 7 over 3. Again, it's okay if x is negative as long as it does not make the argument or base negative. So when you plug negative 7 over 3 into this first log, we're still going to get a positive argument, so negative 7 over 3 is our answer.